As a global fintech company, Iris is always looking to improve our speed, quality and scale. A culture of DevOps is one of the initiatives that we are looking at for this. Last year, Iris sent a few people to DevOps talks. It was a great way for us to build up our DevOps culture, give it a bit of a kickstart and keep us moving. You've had a number of great talks this year. The one on Bitcoin was really good. We had one on MLOps, which was great. Iris is always looking to improve the way we work, and a DevOps culture is a key part of that.
All right, so I'd like everyone to take just a minute to have a look at some of these images. All right. Richard Feynman, fun to imagine. What you've just seen is a class of machine learning algorithms which are called generative adversarial networks. So they have the ability to take in a latent space input, which is any set of features such as some sort of a feature in terms of text. So what it does is it able to translate that into another set of features, and what you're seeing here is basically the ability to generate infrastructure, the ability to generate images. Those images that you've seen prior, they don't exist. Those people don't exist at all. So just a little bit about me. Co-founder of Papertrail. Myself and a good friend of mine decided to start up a small company. Basically, it's research in information technology, particularly around personal information management. So it's really the ability to search for information as human beings do. And we do this by creating features that allow you to search based on things like colors, a search based on things like time and space, where were you, what did you see, and we obviously do this by looking at your previous data that you've been searching in various different tools such as Outlook, such as Internet, Google, etc. I'm also a principal engineer at Telstra, so we run a small engineering group that I guess is pushing Telstra forward into the future in terms of DevOps practices. So I just wanted to sort of demystify some of the terminology used today in this discussion. So we've got machine learning, we've got machine learning ops, singularity, and what does it mean to build intelligent services? So machine learning, you've heard about it, you've been bombarded with various of articles, whether it was on LinkedIn, whether you've read something. Maybe some of your friends have taken some of the very popular courses, such as machine learning from Coursera by Andrew Ng. Maybe you've even delved into writing some algorithms. But machine learning, what is it? It's really the ability for systems to learn from their environments and to improve themselves based on this experience. And they have to do all of this without needing for any explicit code. So much like what Jamie was saying before, he wants to automate himself out of a job. I'm actually trying to do the same, but rather than writing if-else statements, it's really about one neuron at a time. So I guess machine learning in general tries to do this by enabling algorithms to learn from this data. So it tries to make predictions on previously analyzed data. So machine learning generally comes in 3 different models. There is another one, which is a slightly new one over the last couple of years, which is deep learning. And it does this in 3 different ways. We've got supervised learning, which is really around feeding our machines with the already previously seen data, and we label that data. So, for example, you would feed it a stream of, for example, churn data, and you'd say this particular person has churned, this particular person hasn't churned, and based on labeling that data, it's able to infer whether a particular person is likely tend to churn or not. We have other classes of algorithms such as unsupervised. So unsupervised is really trying to understand structures within data and tries to group it in such a way that it sort of makes sense to the data scientists and the engineers that sort of try to unravel what sits beneath that. Reinforcement learning is really around a continuous feedback mechanism where the machine learning system is basically penalized for not doing the right prediction, but is also able to output some commands. So, for example, a lot of reinforcement learning algorithms get used in self-driving vehicles. Okay. All right. Yeah. So, machine learning, where does it sit? It is a branch of AI. AI has been around for quite a while. It's been in the 50s and the 60s. AI generally comes from sort of expert systems, building specific systems that do a very specific thing around image classification, image recognition, but for a lot of those things were handcrafted a few years back. Nowadays, with the introduction of machine learning and the ability to learn from observing the data, we have a new class of algorithms. So where does it sit within the different practices? In this Venn diagram, we can actually see that AI ML sort of sits within the data sciences, general data sciences practice, and surrounding that are sort of a number of sort of ancillary practices that have a direct impact on how machine learning gets realized in terms of the algorithms and the output that they're provided. Machine learning doesn't work without data, obviously. It's absolutely useless, so there is a notion of big data somewhere in there as well. Yep. So singularity, I thought I'll add this slide in. We got sort of 2 types of singularities that people often talk about. There's the black hole singularity, which is a point of infinite density and zero volume. Luckily, we're not going to be talking about that one, but what I wanted to sort of touch upon is the singularity on the right, and it's really the intersection point where human intelligence surpasses or is equal to, machine intelligence surpasses or is equal to human intelligence. So some very prominent figures have been trying to predict exactly what's going to happen when and if machines take over our humanity. So the late Professor Stephen Hawking here has been, I guess, a proponent of making sure that we build the right ethics when we are trying to put these systems into production. And Elon Musk, which is the gentleman in the middle, is... so, yes. On the right, has also been a very big proponent of that. In fact, I think it's sort of taken over his life in the recent months. But I think that we don't yet have to worry about this, as there are some fundamental constraints that machine learning still has to get over. And from my personal opinion, I think it really comes down to the mathematics. I think the existing mathematics around linear algebra and combinatorics and statistics cannot describe certain human interactions, cannot describe certain human emotions, cannot describe certain features that humans exhibit. So I think we still have a quite long way away. I also think that maybe the merger of quantum mechanics and quantum physics may be able to solve this for us, as I think there is a lot more to humans than probability and statistics. And there are some deep underlying hidden variables in our mind, in our brains, that make us who we are, basically. So that's really the concern. Let me go once more. Yeah. Right there. That's something that everybody sort of worries about, particularly some of these more prominent figures. But I think we're far away from that. There are still some fundamental issues that we have to solve. But just because there are certain mathematical limitations and certain structural limitations to machine learning doesn't mean that we can't use sort of the old tools much like we are using them in the current time. So we still have a lot of applications in machine learning that we can expose, as you may have seen. So machine learning ops, how do we get there? That's a question. Obviously, we need talent. That's one of the key components. Learning and development, extremely important. And I'll get to that soon. Value. We need to be able to derive value from applying machine learning. We need to be able to explain to people how machine learning can provide value in their business. And more specifically, I think the business needs to understand what are some of those key problems that machine learning can help them uncover. DevOps, which obviously is what sort of I wanted to get through to today in today's talk, but DevOps is really important with machine learning. I think there is a natural gravitation between the two fields to sort of sit very closely together, much like the merger of testing and operations and development. I think there is a fundamental merger between DevOps and machine learning. So, and the key driver for this is the tools. I guess mathematicians, statisticians, really good engineers have started to really abstract some of these toolings that allow you to expose deep learning and machine learning models from all of those underlying complexities. And it's becoming a lot more palatable for a traditional software engineer to get up and running and start writing machine learning models with some basic learning and fundamental understanding. So it is becoming a lot more sort of pervasive within traditional sort of DevOps culture. We're at Telstra. We're trying to merge the two groups together. We are trying to merge our data scientists together with engineers to build more intelligent systems, and it's really about going back to that learning and development and finding the right talent to propagate the message. Services and tools, like I said earlier on, services and tools are really important. In fact, they're probably one of the more important ones. The reason why is that nowadays I can really quickly get up and running machine learning, and say 2 years ago you would have had to taken certain courses to understand the fundamentals of machine learning, sort of the underlying mathematics, and it was a much harder practice than it is today. But it's sort of synonymous to a lot of us perhaps use Kubernetes as our orchestration management framework, and I don't necessarily have to know exactly the inner workings of Kubernetes to be able to use it. So I think that's the ideology that we're going for. So how do we, what's today's model when it comes to trying to merge DevOps and machine learning practices? So there is a number of different engineering proclivities that we need. So big data engineer, we need to provide the data to somebody. We need to clean the data, and cleaning the data is not a fun job at all. As you can see, the little man here has got a really sad face because it takes quite a long time to clean the data. It takes quite a long time to get the data to the right structure. Machine learning algorithms or general statistical algorithms of any sort just need the data to be extremely consistent. It needs to be normalized. It needs to be, you need to change categorical values into numerical representations. So it's a really hard job. But the data scientists sort of receive those that clean data. They proceed to build those models, and what we get today is we pass those models onto the DevOps guys, ready to go. It's fair to say that data scientists can't build production-ready machine learning models. They just don't have the rigor and the discipline on how to scale software in general. So this is why the two need to merge. So we have the less expensive model. So nowadays we're also seeing sort of big data engineers still very relevant. Except nowadays the data scientists do tend to also contribute to cleaning that data, and also they build the models, and then the DevOps make sure that all those models are served up and in a highly available manner. So we have the cheap model. I'm not sure whether I should call it a cheap model because machine learning engineers are extremely hard to find, but they can replace certain. They can replace a number of DevOps engineers that would generally need to keep a system up and running. So we still again need somebody to provide the data. Data scientists will still clean and build those models, but this time around you can also have a machine learning engineer that actually contributes to building and tuning those models as well as actually running them in production. So I guess we're seeing this this merger of really good DevOps engineers that understand the fundamentals of building good machine learning models, and the sort of the two roles are coming together now to create machine learning engineers. And this is something that we've seen in some pervasive companies such as Google and such as Amazon and the likes. And then we get the no frills model. Just get one guy to do everything. It's like the full stack engineer of machine learning and some. So he provides the data, he ingests the data, he builds the backend infrastructure. Maybe he, she, or maybe a small group of them. They also clean the data. They build the models. They run the models in production. So how do we get to this unicorn factory? How it's an age-old question that's been sort of riddled the industries. How do we get these great people? And the answer is so simple, right? We need to educate. Education is the key to success. Learning and development, extremely important. Large companies underinvest in personal development. Employees are relatively too busy to use their personal time upskilling. And we do have that notion that there is no formal recognition for personal initiatives. But that's changing. It's changing quite a lot. So, learning and development is really about personal development. I know I'm veering sort of off topic, but this is really important. People need to be kept up to date with relevant technologies. I've spoken to some people where there are still engineers out there that haven't that don't understand the concept of cloud, right? So it's quite interesting. So making machine learning fun, so gamifications, hackathons, all that, conferences, sending people out. I think it's going to be fundamentally important for people to start making this shift to build more intelligent services. So customized learning, classroom trainings, study groups, again, conferences, and in large organizations, for example, such as Telstra, dedicated funding is really important for people to be able to go off on their own and study these things and play around with these things, so they can bring it back into the company and the culture as well. So how can you potentially get to a machine learning engineer? We have a number of them in Telstra within the group that I'm in. So I know how to write software. I know how to maintain software, and I can get trained on using certain frameworks. It might take a little while. It might take a few courses, but we can definitely get there. And you yourselves can become machine learning engineers. So value in machine learning, much like any other practice, is extremely important. We need to. It's an extremely difficult conversation with people that may have read a few articles on machine learning or AI and think that the practice can solve all their problems in the organization. It pollutes the notion of what machine learning is good for and what is not good for. But and this is why when we approach the business to seek certain use cases that we can work on within the organization, it's really important for us to follow certain frameworks that will allow us to very clearly articulate what we are trying to do, why we are trying to do it, how we're going to be approaching it, and not reinventing the wheel because the problem may have already been solved. And we need to have a clear motivation behind it, and we need to have clearly defined business benefits with measurable metrics. In fact, our group, our high-performance software engineering, which is part of the Telstra Software Engineering Group, is solely measured on the value that we provide from providing various types of insights into the use cases that we work on. So, and how is value generally realized within the machine learning practices? Much like any other practice, it can be realized immediately. So you work on some data science problem and you provide the business back with some valuable data that they can go back on and improve their process or whatever else they need. Continuous value realization. Fraud detection is a really good one. It continuously provides me value because every transaction that I validate is great for my business, right? Because I'm not losing money. It's over a period of time, so it could be something that's realized over a particular period of time, and then we have to go back and revisit it again because the market conditions may have changed or the technology may have changed, so it's thrown off. It's thrown our models off a little bit. And the future, obviously, right? Some of these things can be applied in the future. So benefits are manifested as simplification. Unfortunately, sometimes it's a reduction of labour, except I don't like to use that term. It's a very ugly term. I think it provides the ability to get the people retrained on higher value tasks rather than doing low value tasks. And I'll get into some use cases what low value tasks mean and over high value. New revenue streams. So a lot of data. We can definitely tap into that data and understand whether there are any new groups of markets that we can explore and offload certain products to people. And the other benefits is we can get services and tools out of some of these practices as well that our other engineers can use. But I think for us within our group we actually focus a little bit less on platforms and tools, but rather how can we immediately provide value back to the business by doing small iterative sort of work. By providing some sort of an insight or maybe small frameworks around it. To do machine learning in the world of DevOps, there are certain considerations and that you need to think about. Doesn't diverge much off today's practices when we are trying to push code into production, but we do need to think about ingestion of the data, right? Because machine learning loves data. We need to think about how do we collect the data, how do we integrate into our various systems that have this data. So we need to build data lakes, we need to build ETL processes. There is a lot of engineering that goes behind this, and it can get quite expensive. We need the people, or at least we need the people to understand how to prepare the data. People need to be able to understand how to encode the data. Encoding really is about turning categorical data, so male, female, Sydney, Melbourne, Brisbane, etc. That needs to be turned into numerical formation because big machine learning algorithms only like to work with numerics. We need to be able to scale the data, right? If you're trying to infer or if you're trying to predict, a label or based on somebody's pay as one of the fundamental features in the model, somebody that's earning $50,000-$60,000 versus somebody that's earning $250,000, it sort of throws off the models a little bit, and you may have a lot of false positives or false negatives. So the data needs to be sort of evenly distributed across the feature space. Training the models, this is an interesting one. Hyperparameters, there can be millions and millions of them. So we need optimized infrastructure to be able to run these models against. So data modeling, parallelization, using those GPU farms. We need training infrastructure. This is where some of these cloud providers are fundamental to the shift. And buying your own GPU farms and installing them in your data centers can get quite expensive. And then the serving infrastructure. So once I've trained my model, I need to serve it to somebody as a front end component, or maybe I need to serve it as a back-end component. Maybe I need to provide that model as an API, and there are many APIs that we can use nowadays in any one of the cloud service providers. They abstract all that complexity for us. CI/CD pipeline, DevOps. How does that look like in practice? How does it look like from an architectural perspective? I do love Amazon. I do love AWS. We use it quite a lot in Telstra for a lot of our stuff. So, how does it sort of look? When you superimpose some of those practices, well, it doesn't differ much, right? I mean, we have new talent that needs to join the team or joins the team, but now there is a separation of duty in terms of the data scientists they would develop the models and they would put the models somewhere for them to be trained and preloaded. And the rest is pretty much the same. You still commit your code, you still go through all of the processes, and you still need to scale your system, and you still need to provide it as a high availability. Up and running really quickly, you can on AWS, and I'm certain that you can do this on Google Cloud or any other cloud provider. The AWS, I'll specifically talk about the AWS machine learning stack. So you've got high-level application services, API-driven services. They fall under different categories. You've got vision, language, conversation. So conversation, as you've seen, I think I might mute her just in case. So we've got Alexa. She falls under the conversational. Alexa runs a natural language processing engine at the back end to infer our speech and our utterances and to resolve intent behind those utterances. So whatever I said before, there was some commands that were driven behind that to tap back into the APIs. Vision and language, so the ability to transcribe information from speech to text and vice versa. And there are some language-based services that you can utilize immediately that will give you some sentiment analysis around text. So you could feed your Twitter feeds in there, and it'll give you a general understanding of what the tweet is about. If it's a positive, it's a negative. Entity extraction, is it a place, is it a person? So it can provide you quite a lot of information, and I'm sure that you can think of many different use cases around that. So now platforms and services, so deploying high-performing machine learning algorithms. They have SageMaker, which I'll sort of very briefly touch upon it. It is a PaaS for machine learning, basically. You start writing a model, and you start training a model, and it handles all of the infrastructure provisioning and scaling, training of the models, and it'll also give you an endpoint, API endpoint, such that you can serve that model to your customers or whoever. And then there is sort of the low-level infrastructure services, which is really about new breed of EC2 GPU-based instances in order for you to be able to train in extremely large data structures. So next slide. SageMaker, notebook instance, you're able to really quickly get up and running, create a project, write some machine learning code, ingest some data, pull it from anywhere. In the back end, it puts it into an S3 bucket. There's some services that take that and run jobs against that data. Not sure exactly what happens underneath, but I would imagine that there is a highly scaled TensorFlow infrastructure underneath, or maybe some other layer of abstraction, or maybe they use EMR underneath to ingest all of that data. But after that's all finished, depending on the amount of data that you have, those models are served up as endpoints, and voila. Tools and services are getting up and running extremely quickly. So from a data scientist perspective, we sort of tend to gravitate more towards Python libraries. Some of the more prevalent ones. So some of the more prevalent ones, scikit-learn, a lot of machine learning libraries in there. NumPy is a very popular framework for working with numerical analysis using Python. Pandas is a really nice data ingestion engine that allows you to slice and dice the data that you pull into your Python application. There's some really pervasive exploratory data science tools that you can really quickly drag and drop data sets, and it'll allow you to have a visual sort of representation of what's going on, and you can chop and change that to visualization. Very important. It's probably one of the more important things in machine learning and data science. You need to be able to visually see what is going on with the data. You need to be able to discern whether one model works against another model. You need to be able to visually see certain clusters of information that are grouping around a specific centroid or a central point. So, and deep learning now is becoming extremely popular. So TensorFlow is a library built by Google, and it's extremely fast. They provide it optimized for mobile phones as well and smaller devices. I've seen TensorFlow run on Raspberry Pi. So you can really start serving up deep learning models from any device. And then there are higher level abstraction libraries, which I sort of was touching upon. I guess TensorFlow is a lot better than what engineers would traditionally have to work with. But Sonnet and Keras, there is Gluon as well. They have further abstracted some of those complexities, which I'll show you later on how we can actually really quickly get up and running in a few lines of code. So, like I said, it's these libraries allow you to really quickly get up and running without actually having to necessarily understand everything underneath all of that stuff. So, it's becoming a lot more accessible. That's the key message here. Get up and running really quickly, really quickly. So, provided that you have virtual environment, you create a Python 3 project, you activate your project, and you install some dependencies. I find that these dependencies are probably all that you need to get up and running, and edit and create your project. So I thought I'll introduce some really quick demos. Something that I've been working on, something that some of my colleagues have been working on. Actually, this is nowhere near production. This is just more for a demonstration. That's something that you can literally whip up right now as you're maybe watching this. So, so we'll go back one step just to. So binary classification. It's a form of a supervised learning algorithm. We feed the algorithm with known data, and we tell the algorithm what the data means. So we supervise it. We tell it. Binary means binary classification is either 1 or 0, or male or female, cat, dog. So in this particular one, if you want to align this capability to, say, one of your service domains within the company, so for example, a customer domain, we have a customer domain, and maybe the function that you'd like to expose would be like churn prediction as an example. So what do? We feed the network a lot of data. We feed it a lot of raw data. So in this particular example, this is churn data. This is not Telstra data. This is just something that sort of whipped up really quickly. But we've got credit rating as an example. Whereabouts the person is, whether they're male or female, and some other attributes, maybe their pay. So all of these are features or feature vectors within a model. And the last one over there, where it's got the 1 and the 0, is what we classify as labels. So in this particular data set, what we're trying to do is we're trying to infer Y with respect to X, X being all of those different features or the rows, for the better word. And we're actually telling it, this customer churned, this customer hasn't churned, hasn't churned, etc. So that's it. We import libs. We've got some libraries that we need to import. We import the data set using pandas, as I've explained earlier. We create a matrix of features and the target label. Target label was 1 or 0, and the features X were the features that we've spoken about before. We cut out some columns that we didn't need, such as row numbers and customer IDs, for example, or maybe their surname is unnecessary. We encode categorical features, so we need to be able to convert the male and the female and those other categories into numerical representation. We split the data set into training and test. I mean, we need to be able to test our machine learning algorithms on real data. So out of the possible 100% of your sample space, there are variations of percentages, how much you want to use for training, how much you want to use for testing. So usually it's an 80-20 split. We split that out. We also make sure that we scale some of those features. Scaling is important, like I mentioned. In this particular scenario, we are scaling everything, especially we are applying scaling to the pay scale or the pay field, because there is a huge discrepancy between one or another. So the models, what they tend to do is gravitate towards a certain correlated set of features that might give us false positives or false negatives, right? And a great example would be, if you're coming from Sydney. Sydney is I guess it's a fairly expensive city at the moment. It might mean that people in Sydney tend to churn more from bigger companies to smaller companies, because the the living expenses are just really great. Right? Whereas somebody that's living in Brisbane, as an example, might not feel the same about that. So what do? So we clean the data, we encode it, we split it, and we scale, and as in scale the features. And we initialize our model. In this particular one, we have a 2-layer model with an output layer. So we've got input dimensions is 11, which corresponds to 11 number of features or columns, and we have 6 units that are coming out, and those 6 units that are coming out come out into a final unit, which is our output, so 0 or 1. Why 6? This is where hyperparameter optimization comes into play. This is where tuning comes into play. Unfortunately, it's not as easy as this. Sometimes people spend quite a lot of time tweaking and find some of the more fine-grained attributes of machine learning models to get them to a certain level of accuracy. So, in this particular one, I've got 85% accuracy, which is pretty good. If you want to get higher, the code would be a lot bigger. So I think there is a direct correlation between your accuracy and I guess the amount of engineering that would need to go into making this a lot more predictable model. And as Jamie has pointed out, I think this is very similar to when we're trying to get to 99.99999. So next one, yeah. So categorical classification. This particular one, unlike the previous one where we have binary classification, categorical classification just means that we are trying to infer more than 2. So it could be, we want to discern between cat, dog, mouse, human, etc. So categories. Where can we use this particular one? In our example, something that I've been sort of working in the background. Again, none of these are production ready. Just pure illustration. So assurance domain, image classification. Yep. We feed it some labeled image data. So the image data is the data that we feed the algorithm is images, and it is a supervised learning algorithm. So we do tell it what the representation of images means. This particular one, what are we trying to do? My modem at home is not working. I don't know what's going on. Maybe I'm an elderly customer. Maybe I'm somebody that's just not technically inclined. I rip out my phone. I take a photo of my modem, and we run it through our image classification algorithm. And what pops out of that is what the problem could be. How do we do it? Now, this is a little bit misleading. There is a mountain of work behind that RASNet 50 at line 19. When I say a mountain, it's an understatement. But luckily, some extremely smart people from a variety of different companies and walks of life have come together to create an already built convolutional deep learning model, or what is called architecture. And they've trained it on millions of images to give us this very simple statement that we can use. There is a little more tweaking behind that needs to be done. The RASNet, deep learning, convolutional deep learning algorithm, has been trained on a million images, but it hasn't been trained on images that represent modem lights. Okay, so what usually happens is that deep learning architectures, they're actually extremely modular, right? Your first set of neurons that take the input get convoluted or transformed into multiple different layers. Those multiple different layers with some inference and some statistical probability try to discern between the very fine lines in the image, right? At the first levels of convolution of a deep neural network, it has no concept of an image. Now, as we convolute further into the deep neural network, there is high levels of abstraction in representation of those images that sort of come into fruition. And then finally, what the learning algorithm can actually do is discern what this image is. In order for, in this specific example, I chop the head, for the better word, off the RASNet model, and I reattach or fine-tune such that I can refeed my images of those modems in and retrain with my images such that I can still reuse the previous or the first convolutional layers, because the hard work has already been done for me in order to understand the nuances of the image at a very granular level. What do? We load, much like before, and we expose an API. So we use Flask to expose this particular API with a /predict HTTP post endpoint, somewhat that conforms to HTTP REST. And that's all right, you can go back. That's it. So we curl, we post that image onto that endpoint, and we get a prediction. Faulty modem, misconfigured, 99%. I mean, of course, if you get a red light or a couple of red lights, you can probably say that something's going on. So, we can go as fine-grained as possible, as we possibly can, just depending on the amount of data that we feed it. Videos. What about the flashing lights, right? What does that mean? Well, we could in theory, and not in theory, but in practice, we could feed a video snapshot of the modem for just a brief moment, and we could also infer some interesting things like looking at the number of blinks, and we can certainly model all of this in our machine learning algorithms. And very quickly, I'm running out of time, but very quickly, clustering demo. This is unsupervised. Something maybe relevant to what Jamie was saying before in the site reliability engineering. Service degradation cohorts. Maybe would like to identify why certain microservices are are exhibiting certain behaviors. So really quickly, yep. I'll actually go back one more. Yeah. That's it, right? So we load some data that we may have produced in any environment, whether it's CloudWatch, CloudTrail, or just syslog. We clean it a little bit. We slice and dice it. We load it into a k-means clustering algorithm. K-means clustering algorithm does exactly this. It clusters based on inference between the different attributes. So in this particular case, I've loaded it some data around payload size versus latency, and what the algorithm tries to actually do is tries to infer some knowledge based around payload size and latency, and it tries to cluster certain services that are exhibiting those correlated behaviors. Now, this is an overly simplified model. Usually, what you would get is hundreds of features that get fed into k-means clustering or any other algorithms, right? But yeah, for this particular demo, it was just really about understanding what the visual aspects of clustering give us in terms of understanding maybe how services work. So courses to get up and running: Intro to Data Science in Python. That's if you do like Python or maybe R or maybe some other language. I mean, it's machine learning doesn't. It's not confined to only one language. You can use it in any language. I wouldn't do machine learning in Node.js as an example, because you do need parallelism. But there are little nifty libraries in Node.js that have been written that can run in front-end mobile applications or even the back-end. Machine learning, like the bread and the butter of all machine learning courses by Andrew Ng from Stanford. Coursera, awesome. I must come clean. I mean, I've actually attempted to finish the course many times over and over again, getting to a certain point and just not enough time to finish. So do try to apply yourself. I'm almost completed, by the way. So, and machine learning crash course, TensorFlow API, really good one from Google. In fact, I'm sure that Jamie can clarify all of the engineers that come through the door of Google, they put them on this particular course from what I understand, and Jamie can clarify that for me. Why? Well, because they see machine learning as one of those fundamental things that should be embedded within everyday software engineering practices. We want to drive towards more intelligent services, and I do want to automate myself out of a job. I just choose not to do it one if-else statement at a time. I'll let the machine decide that for me. So, thank you. First question. All right, great question. No, but the idea is, imagine what's possible. It's not really about. I mean, this was a little gimmick, right? Just to prove out a couple of things, which was, the API, the AI API services exposed by Amazon, which is the natural language processing engine behind Amazon Alexa. In terms of you having the ability to really quickly build utterances and intents to execute your tasks via voice. We actually use it at Telstra for people to just simply ask questions like, are there any available rooms on level 5, right? I mean, these are some of the tasks, mundane tasks that we can automate with these services. In terms of what I did there with Alexa, there probably isn't any value in there, right? However, you could stretch your imagination and build something that could actually provide you some reasonable value where you don't have to interact with the system, rather just ask it, right? It's more about human and machine intelligence in terms of like conversing with your data, right? You're conversing with the data. You're not typing for your data. You're conversing with it as naturally as a human being would. Yeah, so at the moment, I'm not allowed to reveal too much, but we are working with our networks to understand the service performance and why certain services, customer services, so if you have NBN at home as an example, why do certain services exhibit bad performance, given that we don't have access to or understand the NBN network, because Telstra, as much as any other telco service provider, is just an access seeker of the NBN network, so we don't actually own it. So, with respect to our own network infrastructure that we use to serve those requests, connections that people are using through the NBN. So, when you're on NBN, you need to go through a retail service provider such as Telstra or Optus that actually own that infrastructure. So we try to understand whether we can do anything on our end in order to optimize, maybe deload or scale out our networking infrastructure to help our customers achieve peak speeds, peak upload and download speeds. In terms of value, there is definitely a dollar figure that can be put onto this value. Just from a customer's experience point of view, right? And there are other projects as well within the space that we are playing around with, like employee experience, right? The ability for you to get up in the morning and decide whether it would be machine intelligence can allow you to pick whether you want to work from home today or not, based on the occupancy on a certain level that you usually work at, particularly now that the companies are moving more towards sort of future ways of working. Future ways of working and DevOps are sort of don't quite click together. And if you don't come 9 o'clock in the morning, you miss out on a seat. So yeah, we are building some systems to assist our staff as they sort of walk through Telstra doors and go about their day-to-day. I'll be able to use an auto-scaling group that uses it while to analyze and pretty good patterns of responding. When? Anytime. I think you should probably take a look at the log data, and try to infer some knowledge and apply some actions based on that. But I think Amazon's already doing quite a good job at that. So
cool. Thank you.
Thank you.